All right. Worksheet 8 here, we're looking at self-inductance, RL circuit, and reflection. So like what is self-inductance? So an EMF can be induced in a current carrying coil by changing the current magnetic field, magnetic flux that itself produces, right? So in all previous cases, the field would come from an external source. So you would have like a magnet there that would just exist there, or an electromagnet, right? But with self-inductance, the change actually occurs within the coil itself. So we'll see how that's applied. And we can see that we have the equation for self-induction, inductance, RL circuit, and then we can move to our law of reflection, right? And more powerfully, I would say, is Snell's law. So, like we've gone over Snell's law at this point before. And what does it look like? I think like it's best to visualize it in like a diagram sense. So it'd be something like this, right? So you have light is like coming in like this, and then it comes out, let's say like this, right? And between them, you're going to draw this straight perpendicular line right here, right? And that's called the normal. And really important are these angle thetas, right? Okay, so in here would be, let's call it N1, and out here would be N2, right? So, we recognize this part of the equation, but we need to recognize those thetas. So the question is always like, is theta one here, or is it over here? It will always be the one that is touching this perpendicular line called the normal, right? So always touching the normal. Again, so that's theta one right here. And what about like over here? Is it this? No, it's the one that's touching the normal. So that's theta two. Okay, so these ones are pretty straightforward here. The only thing I would add is you don't even need to do this, but like if you just want to be double careful about it, is when you go from low to high index of refraction. So let's say this is equal to 1 and this is equal to, I don't know, 10, right? So when you go from low to high, you can see the vector is going from low to high here. It bends towards the normal. So instead of this vector pointing out like this, it bent towards the normal. So it'd be kind of more in line with where it is now. And then the inverse is true, right? If it goes from high to low, it would be bending away from it. So let's say if the light was in fact going this way and like this way, it'd be something like this, right? Further away, only if that was the case. So again, if you go low to high, you bend towards the normal, and high to low, it's away. Yeah. Oh, actually, I'll leave this here. It's kind of helpful. Okay. And let's just look at the first question. So in Q1, we're given a current in a coil is increased uniformly from 0 to 20 amps in 4 seconds. The induced EMF is 12 volts. We want to determine the self-inductance of the coil. And we want to determine the energy stored in the coil when the current is equal to 20 amps. So he didn't actually give you guys the equation for solving for the energy inside an inductor. So I'm just going to give it to you. I asked him about it. He said, they're expected to know it. It'll be on the formula sheet. I didn't see it on the formula sheet, but I'd rather you have it and not need it than need it but don't have it. So, self-inductance. Which equation are we going to use? You better believe it's the self-inductance equation with a delta I over a delta T, right? So what does that come out to be? It's going to be final minus the initial divided by T, right? So we're going to rearrange this equation to solve for L now. So L is going to be equal to times T, the initial. We're going to do some cancellations. Things come out. L is going to be equal to 2.4 H. Okay. So, this is going to be equal to 12 right here. This T is equal to 4. And then, the final is 20. The initial is 0, so it's equal to 20. So, yeah, let's work with things. It's part B. And in part B, we're asked that to solve for that, determine the energy stored, so that U. And U is equal to 1/2 Li squared. We just solve for L. We're given the current, 20. And now we can solve for the energy stored in there. So U is equal to 1/2, 2.4, 20 squared. U is equal to 480. All right, next. Question 2. So In question 2, we have a coil that's connected to a 12-volt battery. After 0.2 seconds, the current through the coil is 50 milliamps. After 10 seconds, it's 0.3 amps. We want to determine the time constant, that's that tau value. We want to determine the resistance. And we want to determine the current after 0.5 seconds. So let's start by using our RL equation, right? So Q2, which is going to be equal to, let's call it Imax, right? Imax is equal to I2, where I2 is equal to 0.3 amps. And now we can solve using I1 is equal to I2, 1 minus E T divided by tau. Okay. So let's see. Let's get the currents on one side. So I1 over I2 on one side. I1 over I2. That leaves 1 minus E to the minus T over tau. Now, let's bring that 1 over. So we'll do, actually, we'll bring the E over, and we'll bring that these stacked currents to the other side. So we'll say E, like this. We're going to natural log both sides. So ln. Okay, we're almost there. We just want to solve for tau, so we're going to have to, flip and then divide, and we'll get that minus T over ln 1 minus I1 over I2. As such, tau comes out to be 1.097 seconds. Awesome. All right, we want to determine the resistance in the coil. So this should be a nice throwback here. We're going to use Ohm's law. So V is equal to IR. R is equal to V over I2. R is equal to 40. Cool. And then in part C, we're asked to solve for the current after a certain amount of time. So we need to solve for current as a function of time. So IT here, I max, 1 minus E to the minus T over tau, like this, okay? And then, what's I max is equal to I2. We talked about that before. 1 minus E to the minus 0.05, oh no, 0.5, divided by tau, which we previously solved for. Okay, and the function of time is represented by these variables right here. So now we just plug everything in, Oh, might as well write this as what it is, right? So 0.03. I don't know why I keep saying that. It's just 0.3. So as a function of time, we'll see that it equals 0.1098 amps, right? And that tau is a measure of how fast it's charging or discharging, right? So that's why it's consistent and kind of intrinsic to the system itself. That value tells you like its capacity to charge and or discharge. Okay, where tau equals L over R. All right, so that's Q. That's Q2. Let's move on to Q4. And that's because I'm skipping Q3 for now, and I will come back to Q3 at the end, calling it the special question per special request. I'll solve that one. So we can stay tuned for that at the end. So what I'm actually do here is I'm going to pause real quick and draw this one out. This is kind of a detailed drawing. All right, we're back here. So let's see. So here we have Bob standing at the edge of a swimming pool, and he's holding a laser pointer 1.5 meters above the ground. He's like shining it in. And we have this like whole setup, right? So he's holding it at some angle. Let's call that theta 1, right? It's holding it at some angle. And then it enters the water at some angle. So now where do we draw the angle? I'm going to draw it right over here, right? Remember, it's always in respect to that normal. And you know what? Actually, I'm just going to call this theta 1. Because if you have a good eye, you'll see these are alternate interior, right? And then over here, I'm gonna call this one over here theta 2. Okay, we have our whole setup going here. We're solving for D, right? This guy. We don't know what it is, but we know it's made up of the sum of L1 plus L2. So that's how far he is from where it hits the water. And then from L2 is how far, after going into the water, how far it goes. So the first thing we need to do is solve for theta 1. How can we solve for theta 1? We're going to go L1 over H1, right? Theta 1, do inverse tan, all that action, comes up to be 63.43. Okay. So using this now, we can use Snell's law to solve for theta 2 because we know n1 sine theta 1 is equal to n2 sine theta 2, where n of, this is n2 down here. It's n of H2O, which is equal to 1.33, I believe. Yeah, 1.33. Okay, so we need to get theta 2 isolated onto one side, which is going to be equal to sine inverse of sine theta 1 over 1.33. Theta 2 equals 42.3 degrees. All right. And then we can solve for L2 using tan theta 2, which is equal to L2 over H2. Therefore, L2 is going to be equal to H2 tan theta 2. L2 equals 2.27 meters. Now what you have to do is L1 plus L2, which is equal to 3 plus 2.27, which is equal to 5.27. 5.27 meters. Box that guy. So that one, that one's pretty easy now. Let's kick it up a notch with number 5. Yesterday I had a really bad allergic reaction. All right, let me start from the beginning here. So Dr. Jaggers, awesome professor. You guys will have him for biochem. And if you're lucky enough to be in his nutritional biochemistry class, you'll have him there too. Anyway, he bakes for you guys. Biggest win, okay? Awesome professor, biggest win that you get the baked goods. He makes this dessert that looks so good, but I'm being a gentleman. I'll let everybody else have it. And then I'm like, if there's one extra, I'll grab it. This time, I missed it before, they had it. I'm like so excited. And I had it. I came to my apartment, and even the front gate of the apartment was broken. So I couldn't even get in. So I was waiting. I was like, I want to eat this awesome thing. So I'm waiting. I finally get in, come to my room. I'm so hyped, wash my hands, sit down, take a bite. I'm like, wow, amazing. Amazing. And then, whenever I eat something I'm allergic to, I begin to feel it. And I'm like, weird. I'm starting to feel a reaction coming on. But he said that there's nuts. He said there's peanuts in there. And I'm not allergic to peanuts, so I'm fine. So I keep eating this thing. And the allergy is just getting really bad. My eyes start swelling, I'm getting hives on my face. And I'm like, all right. I open it up and I see there's also cashews in there. But he only said peanuts because, peanuts is a lot more common than cashews. So yeah, my eyes were swollen. I was so itchy, rough night. Anyway, my throat's still a little scratchy. Or not scratchy, it's more it feels like I want to itch the inside of my throat. Gross, but yeah. Anyway, sorry, I wasted everyone's time just now. All right, so here we have an equilateral triangle. Okay, and we're told that a light enters the 60-60-60 prism, and the index of refraction of the prism is 1.6. We want to determine the angle theta the light beam exits the prism. Okay, so out here, we assume it's air, right? If they don't tell us, we assume it's air. So n equals 1. Inside, n equals 1.6. And we have this light coming in, right? First off, they tell us that it comes in at 45 degrees, so we know it's coming in straight up, right? And it needs to be perpendicular here. Wait, I am recording the iPad. Oh my goodness. It's going like this, right? And this is 45 degrees. Okay. And remember, this normal vector is always perpendicular to the surface it is entering. So that's why it's 45 here, right? So once inside, it's gonna, go down like this, and it's gonna hit this position. Again, we draw the normal, which is perpendicular. And then the light comes out on the other end. Let's say it's like this. I truly don't know Oh, n equals n. True, but not helpful. Something like this, right? And remember what I told you, like when he goes like low to high, it bends towards or away. Like that's just kind of they don't ever like they don't ever look for that. As long as your diagram is correct, it's good, right? So the first thing we're gonna do is we need to, well, how should I do this actually? I'm gonna label each one first. So this is, let's call this, let me change colors here. Let's call this theta 2. Let's call this theta 3. Let's call this theta 4. Let's call this theta 5. And this one we'll just call 5. Something like this. So I ordered them in this way for a reason, right? So we have the index of refraction of inside, outside. We know the angle at which it enters. So we're going to solve for, what's it going to be? We're solving for theta 3 or theta 2? Theta 2, remember, you always solve for the one or draw the angle for the one that is touching the normal vector. So we'll use Snell's law, where it's n of air sine theta 1 is equal to n of the inside of the prism. I'm going to call it np sine theta 2. We know everything except for theta 2, so we can solve for theta 2 by doing that inverse sine sine 45 divided by 1.6. And theta 2 comes out to be equal to 26.23 degrees. All right. With that, we can solve for theta 3 because, remember, it's perpendicular to the surface, so therefore it's a right angle right there. So if we do 90 minus 26.23, we get theta 3, where theta 3 is equal to 63.77. Okay. And now, this one is where it gets a little, actually, let me write this real quick. This is where it gets a little tricky here. If you have a really good eye, you'll see that there is, in fact, a triangle produced right here, right? Where we know this angle, we know this angle. We're looking for theta 4. So let me get rid of that triangle there. We can say that 180 minus 60 minus theta 3, 63.77, is equal to theta 4. Theta 4 is equal to 56.23 degrees. All right. With theta 4, we can kind of use that same principle where we know this is a right angle. So we can do 90 minus theta 4 is equal to theta 5. So theta 5 comes out to be equal to, we just solve theta 4, plug it in, it's equal to 33.77. Again, we're now exiting the prism, so we're going to use Snell's law. So NP, which one do we use? Sine theta 5, this is the one touching the normal, is equal to N in the air, call it N air, sine angle B right here. That's what we're looking for. We're going to have to do some rearranging. This is now something we've done many times. Sine inverse, 1.6. That's the prism index of refraction. Sine 33.77. That's the theta 5. And then, divided by, well, we don't need to do that actually, because it was 1. So 5 comes out to be 62.8 degrees. Bam. Cool. Now, let's do the special question. I think I removed it from the worksheet, so I'm going to screenshot it and put it back into this, and then we'll read it together. So allow me to pause real quick. All right, so we're back with the special question. It's pretty long here. I'm just going to go through everything A through, what's that? H. Okay. All right, part A. So, we have 3 resistors. We're given their resistance values. They're connected to a 24-volt battery. The inductance of the inductor is 6H. And the switch is closed at time is equal to 0. So just after the switch is closed, determine the current I1. So we know where I1 is acting. So how can we quickly find that? This should be a nice throwback. You can just do a loop, right? Okay, so at this point, the switch is closed. I'm going to draw that in. And henceforth, it will be closed. So switch is closed. We do a loop, call it loop 1. So remember, it all has to equal 0. We're working our way up this way. We start from the minus terminal to the plus, so it's plus 24. we go down, so it's minus, what's R1? 8 I1. Solve for I1. I1 is equal to 3 amps. Bam, done. Part B. So you want to solve for I2 immediately after closure. This is where, like, it's by definition, immediately after closure, you treat an inductor as if it's an open circuit. So therefore, there is no current acting here. Okay, so that's kind of the point of this part. Immediately after closure, this inductor, it's almost as if it doesn't exist. It's just open. It's an open circuit. Okay, so 0. Part C, the rate of change I1 over delta t. Okay, so, well, you know, it's immediately after the closure again. So at time equals 0, anything, it's like there's a 0 there. So divided by 0 is equal to 0. So delta I1 over delta t is equal to 0 amp per second. All right, part D. Now we're asked for the rate of change I2 over delta t immediately after the closure. So why not do a loop again, huh? Do a loop, call it I2. So with I2, we start behind the battery, so 0, plus 24. We hit the resistance R2 resistor first, so minus 12I2 minus, and then when you do an inductor, right? So when you do the loop through an inductor, it's minus L of its I2 divided by T, right? So this is the variable of interest we're solving for. So we already showed why this is equal to 0. We bring 24 to the other side. So we can say L delta I2 divided by, oh, might as well bring that to the other side, make it positive, equals 24. Divide both sides by L, where L equals 6. So therefore, I2 over delta T is equal to 4 amps per second. So the things to remember. Okay. Current I2 is flowing like this. Through the inductor, through the inductor, in the same direction as the loop, so the current's agreeing, and you treat the resistor and the inductor the same way, right? They have the same behavior in that they have that minus sign. And this is what you plug in. This comes up, pops out as 0, solve all the way through, you get 4 amps per second. Now, we're told that the switch has been closed for a long time. So in a steady state, that means steady state, right? So in a steady state, DC current will flow through an inductor. The inductor will act as a short piece of wire, right? So in the beginning, it's as if it's not even there. It's like invisible. It's just open circuit, no current. However, after the fact, it's going to act as a wire. So as a wire, you know, maybe I'll be better off just drawing it, right? So let's redraw it. Pardon my, oh, geez, my speed drawing here. But something like this, something like this. Okay, so steady state, where this is, you know, this is the 8 ohms, this is the 12 ohms, this is the 24 volts. Switch has been closed for a long time. I1 is right here. This is I1. And this is I2. I'll put I2 in blue. This is I2. And we're at steady state, so it's a wire, right? It's like not even there anymore. So we're asked now to again solve for the I1 value. Let's call that I1 prime, and let's call this I2 prime, so we don't get mixed up. So we're on what, E? So in E here, we're asked to solve for delta I prime, where, well, actually, it's the same thing, right? So if we do a loop again, it's the same business. Same loop, nothing's changed. Again, I1 prime is equal to 3 amps. Okay. Okay. Where this is I1. Sorry, I wrote that in blue. It's kind of confusing, right? So I1, we just solve for that. Now, in F, we're asked to solve for I2 prime. This is going to be different. We have to do a new loop. Let's call that loop 2. So in the same way, you know, start behind the battery, it's equal to 24, work our way through. And what's the only other circuit element we hit? It's that minus 12 I2. So solve for I2. I2 is equal to 2 amps. Their inductor is gone. At steady state, you treat it as a wire. Okay. G. We're asked for that change in current over time with respect to I1. So it was before 3 amps. It is now 3 amps. So what's the change? Trick question. There is no change. Same thing. All right. However, in H here, we're at steady state. So remember, at steady state, what is the inductor? It's a wire. There's no change in current in the wire. The wire is the same. Again, equals 0 amps per second. All right. So this one is less about like, it's intimidating, right? It's like, oh my God, it's like 8 parts. But you'll really see it's an application of definitions where a lot of the things end up being the same. So when the wire first closes, this whole thing right here is as if it's not even there. It's like opened, no current on that side. After it's been closed at steady state, it's treated as a straight wire. Okay. That concludes worksheet 8. Sorry for the delay on that. Alex, you're welcome. I finally solved this question after 10 years. All right, thanks for watching.